Hello everybody, welcome back. We're now ready to use the tools that we learned on stochastic games for applications in dynamic control of advertisement in social networks. The model that we present now is the same as the one we had for the semi-dynamic control, and the difference will be here that we shall use control all the time. So there are n content providers, we can call them players or seeds, and m potential destination. A destination small m is interested in the first content that it will be aware of, and eventually if other contents of the same type arrive, it just ignores them. We again introduce the popularity of a content. Content I arrives at a destination after a time exponentially distributed with parameter lambda I. This lambda I is what I call here popularity. Something more popular will have a larger lambda I, and that means that the expected time till it gets the first copy from source I is small, 1 over lambda I. The goal of the seed is to maximize the number of destinations that have its content. We call this a dissemination utility. It is just the number xi of t, where t is some very large time. Player n can accelerate its dissemination process by a multiplicative constant a, at a cost c of a. We define the dissemination utility of player I to be g of xi. This will serve as a terminal utility. We shall also introduce the difference zeta I of xi as the difference between the terminal utility evaluated at xi plus 1 and the terminal utility evaluated at xi. When using this as a running utility, instead, if we use zeta as a running utility, then the cost is equivalent to using g as a terminal utility. And this is an important trick that we shall use in order to simplify considerably the problem. Assume that the state is x, and by that I mean that xi destinations have a copy of the content from source I. X is the vector of the different xi's. Each one of the m destination will receive a copy of a content from source I after an exponentially distributed time with parameter lambda I ai. So this is what I meant by ai being multiplicative. It can accelerate the process of dissemination by multiplying the parameter lambda I. Now we shall assume throughout that ai is within some interval, given interval, with the maximum value a. Yet, if some destination already had the copy, then this transition will not cause any change in the state. So this is what we call here fictitious transitions. Define ei as the vector of where all entries are 0 and only entry I is 1. The dimension of this vector ei is the number of players. So a real transition from x to x plus ei occurs at the rate of m minus the number of destinations that have already a copy times lambda I times ai. Recall that our goal in uniformization, which we use here now, is that the rate of transitions be the same, not only at all states, but also for all actions that are used. So now let A be the largest possible action of a player. And we define the total transitions rate as lambda equals m times A times the sum of lambda i's. So next transition now occurs after an exponentially distributed time with the parameter lambda that we just defined. This rate lambda is indeed larger than the rate out of any state. It is constant. It doesn't depend on the state or on the action. Real transition occur at rates that depend on states and depends on actions. So in order to get the real transition rate unchanged, we have to define transition probabilities to remain at state X and the transition probabilities for real transitions. So once there is a transition, the probability for going from X to X plus EI is defined as the ratio between M minus X times lambda I times AI divided by lambda. This guarantees that indeed the rate of real transitions out of state X when using actions AI is unchanged, is the same as in the real process. This is what uniformization is about. Now, definitions of the immediate cost and immediate reward. We have immediate costs for the acceleration process, which we write as C of A. This is the cost for accelerating the dissemination rate by a multiplicative constant A. We define dissemination utility of player I to be some terminal utility G at a very large time. It's a function of how many copies of the content from user I, how many copies have arrived at different destinations. So it's a function of this G, of this Xi. It will be useful to express this terminal utility as the sum of the utility between time n and n minus 1. So these differential utilities zeta I, just the difference between G evaluated at step n plus 1 and G evaluated at Xi at step n. We now introduce the dynamic programming operator. So VIX is the total reward till we hit the absorbing set M for player I if we start at state X. So it is given by the maximum of the acceleration cost, which is with minus because we maximize here a cost. After writing the cost for acceleration, we would like to write the utility for dissemination, G. But remember that this GI is the utility at the final time, at the time where we will reach the set of states M. So what we propose to do here, to write Gi of x time t as the summation of differences between Gi at time s plus 1 and s for all s smaller than t. So what we have in the dynamic programming is the difference between the utility at the next step minus the utility at this step. So what you see is the utility at this step, Gixi, which appears immediately after the cost for acceleration. The utility at the next step should appear after we take all possible probabilities to go to different states in the next step. So this is why it appears after this summation. In addition, after the summation, we also write the value evaluated at the next at the state at the next step. So here again it is evaluated at each possible next step state times the probability to get there. Now, after the summation, there is also the evaluation of G and of V in the case we don't move to any place next step. So in case we have a fictitious transition. So the last term that we have here, the 1 minus something times V plus G, corresponds to the probability that there is a transition from the state X to itself. So it is 1 minus the probability to have a real transition to states other than X. This is what we wrote there. So now the dynamic programming can be written as 0 equals the maximum evaluated over all AI of ZIXA, where ZIXA can be expressed as in the bottom line. Some simple algebra yields the expression for the last line from the first equations that we have here for VIX. We now present the main results. So there are three main structural results that we get. The first one states that if the dissemination utility is linear, then the problem becomes one-dimensional. The state space can be reduced from vectors, a set of vectors which have dimension I, the number of players, to a one dimension. What we do, instead of saying how many we have from each source, we only have to keep in memory how many destinations have some content, no matter from whom it is. The second result is that the dynamic programming equations in fact simplifies once we have this one-dimensional reduction. We can formulate explicit M matrix games, and the equilibrium at matrix M in these games is the equilibrium for the original game at state M. In other words, we can solve the dynamic programming separately, at least at each step. The third result states that if in addition the acceleration cost is linear in A, and this means that it has the form of gi times A minus 1, because recall that we don't want to see any costs incurred if we do not accelerate, and if we do not accelerate, then A equals 1. So for A equals 1, we want this to be 0. This is why we subtract the 1 there. Under this structure of the acceleration cost, the equilibrium policy for player I is the threshold one. By that I mean, first, that there are constants gi over lambda I, so that we take one action below this constant, if the state is below this constant, and another one if it's above this constant. Now, what are these two actions that we take? Just the extreme ones, the smallest or the largest. So now the question I would like to ask you is, what do we do? Do we take the largest action if the state is above, or do we take the smallest if the state is above this threshold? Well, it turns out that we take turns out that we take the largest possible A for states below this threshold, and otherwise the smallest possible a. Second question, do we spend more on unpopular file or do we spend more on advertisement in popular files at equilibrium? The answer is, of course, that we have to advertise more popular files. Why? Because we pay the same amount if we double the rate of a popular file or we double the rate of a non-popular file in terms of the acceleration cost. But if we advertise a popular file, this will bring us a much larger increase in the dissemination utility, because many more will see it, because we go from a large lambda to an even larger one. So that is the intuition here. Why does this work? Why were we able to aggregate the states? We use the theory of state aggregation that I introduced early in this tutorial. We aggregate all states that have the same cardinality to one state. Now let us check that the conditions hold. So the condition on the transition probability. The transition probabilities indeed depend only on the cardinality of x. Here they are. The important thing is that they do not depend on particular x's within each aggregate of states. Now the acceleration immediate cost does not depend at all at x or at xi. Now we saw that we know that the reward here, the final reward, the final dissemination utility for player I depends on the ith component of x. So it does not satisfy the rules that we said. But this is precisely why we change the terminal reward into a running reward, and running differential reward. If the dissemination utility is linear, then once we go to the differential utility, then the differential utility does not depend anymore on the ith component of x. It is just a constant. Now, how can we interpret the aggregated problem? So first define Qx as the summation that we see above. So it is the probability at state x to have a real transition from state x to another state not x. So this probability Q, of course, will be a function of x, and also the A, the action A here, is a function of x. So we define this for a given state-dependent policy. Now in the aggregated problem, when we are at state x, then at each slot, the state either increases to x plus 1 with probability qx, or else it remains at x, at state x. Since any policy will take us through states 0, 1, and so on till m, and I speak now about the aggregated space of states, of course, we can decompose the dynamic game into a set of m different games, one played at each one of these states, where in the mth game, player I maximizes the total expected utility, UIM, if we were initially at state m, till we get to state m plus 1. The threshold policy was in a special case in which the costs for acceleration was linear. We now give the structure for a more general cost for acceleration. The time it takes to go from one state m to the state m plus 1 in the aggregated model the exponentially distributed with parameter, which is the capital M minus small m, times the summation of Aj lambda j. This follows from the fact that it can be written as a geometric sum of other exponential random variables. The probability that the origin of the next content to be delivered is player I is simply Pi equals the ratio between lambda I AI and the sum over all players j of Aj lambda j. At state M, the players play a game where the utility for player I is UIMA and is given as the following sum of two terms. The first corresponds to the cost for acceleration and the second for the utility for dissemination. The cost for acceleration is CIAI multiplied by the expected time we spend at state M. And since it's exponentially distributed with parameter theta m, it's just 1 over theta m, this expectation. So UIMA can be considered as a matrix game or as a concave game between I players, and there are m such games that are played, one at each state. And it is the solution of this game that provides us an equilibrium policy, state-dependent policy, in the original game. We have seen potential games in many places already in this talk. The game here is also related to a potential game, but it is not exactly such. The potential will appear in the dynamic programming equation, which transforms an equilibrium over policies to a set of equilibria over actions at each state. Recall that a policy is an equilibrium if for each player I, it achieves the max in the following dynamic programming equation, which is in fact a set of equations, one for each state x. Now we discussed equivalent game. We said that an action is an equilibrium to with given utilities if and only if it is an equilibrium in a game in which we add some constant, or we add to the utility of player I some terms that depend on the actions of player j. So here we can say the same thing. If you consider some player I, its action achieves the max in the dynamic programming equation if and only if it maximizes Zi, where Zi is the same expression that we had in the dynamic programming, but instead of taking the sum over all j, we just take the ith element of the sum. Now the summation over all I of Zi turns out to be a potential in the dynamic programming equation. Now we know that equilibria for the dynamic programming set of equations maps to a stationary equilibria in the original game. And therefore, since the equilibria for the dynamic programming can be obtained as a global optimization problem that does not depend on a specific player, and since we know that the maximizers in dynamic programming are achieved by pure actions, we conclude that indeed there exist pure stationary strategies in the initial game. So this is what we learn from the fact that there is a potential in the dynamic programming formulation. So now assume that we don't have any information. Then what we do, we take the expectation of xi's as the different component of the state space. So the state space itself is an expectation now. In general, in control problems, it is not possible to take expected states as state when we do not have information, simply because the cost is not a function of the expected state. On the contrary, it is the expected cost of the state which is usually used as objective function, which we minimize in control problems. The reason it works in our case, the reason we can use the expected state as state when we have no information, is that costs are linear and the dynamic is linear. So the expected state is only function of previous expected states and the previous actions taken. And the expected cost is simply the cost of the expectation. We can exchange the order between cost and expectation here because of linearity. The evolution of the expectation follows one of our models that we saw in the population dynamics models. The one for finite population, which is M in this case, and where we have no virality in the network. This gave a concave increasing exponential behavior that had an asymptote M. This, of course, was for a fixed value of lambda i's. Here we accelerate the lambda i's by multiplying them by some multiplicative factor wi t, which may now vary from one time to another. Now note that although there is a lot of randomness in the problem, when we go to expectations and describe the model as a function of the evolution of the expectation, there is no more randomness. On the other hand, the dynamics is now in real time and in continuous time. It's not in slotted time anymore, nor in embedded instance. Games in which the state's evolution obeys differential equations, in which the control are parameters, are called differential games. So what we get is a special case of a differential game. Differential game can also be solved using a dynamic programming approach. We shall not do it, but we shall instead go directly to state the results that we get from this analysis. Here again, the state space collapses to dimension 1. So we can solve this problem by a state which is just the sum of components xi of x. The equilibrium at state M is obtained as an equilibrium of mth matrix game, but now M is a real number. So in fact we need to solve a parametric matrix game where the parameter lies within a whole interval, real interval. The two previous results that I mentioned require that the utility for dissemination be a linear function of the state. If further the acceleration cost is linear, we again obtain the same threshold type of policies as before, and with the same values of the threshold. So we get exactly the same behavior as in the problem where we had full information. This ends the presentation of the model on stochastic games for advertising on social networks. Now I would like to say a few words about references. You can Google me and you would land on this page, which you see here. Now, there is the rightmost icon, which is called AGGREGATED. If you click on that, you get the following page. This will bring you to the following page that includes many of my videos, including some that went to international competitions. And what's more important is the list of publications with the PDF files that you can download. And that includes the model that I just presented here and many others, which I didn't present so far. Before ending, I would like to propose to you a video of mine on Avignon, which is the town where I lived in France. It's about the Pont d'Avignon, the Bridge of Avignon, which is a very famous song about a bridge where people dance, a bridge that is broken and you cannot use it for doing anything else but dancing.